Hello and welcome to the session. In today's session, we will see the design of a shaft. So we have a question here. A shaft is supported by two bearings placed 1 meter apart. So first let us draw the space diagram. So for that, I'll draw the shaft here. So the length of the shaft is given as 1 meter and it is supported at the ends. So I'll show this is supported at the bearings, at the ends. The length I'm marking it as 1 meter. So this distance is 1 meter, it is given. Now it is given that a pulley having 600 millimeter diameter is mounted at a distance of 300 millimeter to the right of the left hand bearing. So this is a left hand bearing. So from this point we have to take a distance of 300 millimeters to the right. So proportionately I'll mark a point here. So this distance is equal to 300 millimeters. Now the diameter of the pulley, it is equal to 600 millimeters. So proportionately I can draw this pulley, I can represent this pulley. So this is a pulley. I'm naming this pulley as pulley A. And then the maximum tension acting on this pulley is given as 2.25 kilonewton. So that means I can represent that as TA2, TA1. That is a tension acting on the tight side of the pulley. And that is given as 2.25 kilonewton. Now, next it is given that another pulley of diameter 400 millimeter that is placed at a distance of 200 millimeter to the left of the right hand bearing. So this is our right hand bearing. So from this point we have to take a distance of 200 millimeters to the left. So this distance is equal to 200 millimeter. This is 200 millimeter. And the diameter of the pulley is 400 millimeter. So the first pulley A is having a diameter of 600 millimeter and the second pulley is having a diameter of 400. So proportionately that is a smaller pulley, so I'll represent it as a smaller rectangle here. And I'm naming this pulley as pulley B. And the tension acting on the pulley, it is not given. But it is given that it is driven with the help of an electric motor placed horizontally to the right. So here the power transmission is taking place in the horizontal direction, but in this first pulley the power transmission is in the downward direction because it is given that the pulley drives another pulley having a maximum tension 2.25 kilonewton directly below it. So here the power transmission is vertically downward. Here this power transmission is in the horizontal direction. Now I'll name this point a bearing, the first bearing point as C, and this point it is D. Now I can complete this side view of these two pulleys. That is, first one, the larger pulley, that is pulley A, a larger circle. This is pulley A. And another pulley, that is a smaller pulley, smaller circle, and this is B. Now we know that in the pulley A, the power transmission is in the downward direction, so I can represent this tension acting on this pulley, and I can mark it as TA1 and TA2. That is the tension on the tight side and the slack side of the pulley. And in this TA1, it is given as 2.25 kilonewton. Now in this pulley B, we are having this force in this direction, horizontal direction. So I'll mark it like this. It is TB1 and TB2. That means it is a tension acting on the tight and slack side of the pulley B. Now it is also given that the angle of contact between the pulley is theta is equal to 180 degree. Theta is 180 degree, that is equal to pi radian. Then the coefficient of friction mu is given as mu is equal to 0.24. We have to design a suitable shaft, assuming that the torque on one pulley is equal to that on the torque on the other pulley. So that means the torque acting on the pulley A, that is same as the torque acting on the pulley B. So these are the data given in the question. So some of this data we have to assume it. We have to select suitable material and the stress limit values from the data book, and the combined shock and fatigue factor. This data we can assume it from the data book. So designing a suitable shaft means we have to find out the diameter of the shaft. So to find out the diameter means what are the equation that is available for finding this diameter. Diameter of the shaft, I am representing it as D. So for that we have to first understand what are the type of force that is coming on this shaft. So we know that the shaft is continuously rotating. So that means there is a twisting moment acting. So twisting moment, I'll represent it as capital T, that is a twisting moment or torque. So this will induce a shear stress, that is toe. This will induce a shear stress. So I'm representing this torque as T. That will induce a shear stress represented as toe. So we have a shear stress acting on this shaft. The next one is, we know that here the force is acting in the vertical direction, in the downward direction. Here the force is acting in the horizontal direction. So we know that there is a bending for the shaft. So if I have a beam like this, and if it is supported at the two ends, and if I apply a load like this, the tendency of this beam is to deflect like this. It will deflect like this. So you can see here, this is the maximum deflection. The bending is maximum at this point. Now we can see that the bending stress, so here a bending stress is induced here, bending stress, because of the bending of the shaft or because of this load acting on the shaft. We have given two pulleys mounted on the shaft, A and B. In this case, we are neglecting this weight of the pulley, otherwise we have to consider that force also, but in this case that weight of the pulley is neglected, but we have a force acting in the downward direction, so that will cause the deflection of the shaft. So here it is the bending of the shaft. So at this point, the stress acting on this section, the bottom portion of the shaft, it is a tensile stress, and at the top portion it will be a compressive stress. Compressive stress. So because of this deflection of the shaft, you will be experiencing two types of stresses. One, it is a tensile stress acting on the bottom portion of the shaft, and the second one, it is a compressive stress acting on the top portion of the shaft. And both the stresses are the normal stress. So bending, because of bending, we are having a normal stress. So I'll represent this bending moment as Bm. So this bending, it is moment, and that is producing a stress, normal stress, sigma. So we have two types of stresses acting on the shaft. The first one, it is a shear stress because of the torsion, because of the twisting of this, because of the rotation of the shaft. The second one, it is a normal stress sigma, and that is because of the bending of the shaft. That is because of the tension acting on the pulleys. So these two we have to consider. And what is the equation we have considering this twisting and bending moment? So I'll take this data book page here. So this is the equation we are having. From page number 51, we have two equations, that is 3.6a and 3.6b. The first equation is, according to the maximum normal stress theory, we have D is equal to 16 by pi sigma max into Cmm plus square root of Cmm the whole square plus Ctt the whole square. This term we don't have to consider. This is applicable for the hollow shaft. Since we are designing a solid shaft, we have to take only this section. And similarly, according to this maximum shear stress theory, we have the diameter is equal to 16 by pi tau max into square root of Cmm square plus Ctt square raised to 1 by 3. So I can write this equation here. The diameter can be found out using two theories. The first one, it is the equation is 16 by pi into sigma max into Cmm plus square root of Cmm the whole square plus Ctt the whole square, the whole thing raised to 1 by 3. The second one, it is D is equal to 16 by pi into sigma max. Sorry, it is not sigma, it is tau max. So it is tau max pi into tau max into square root of Cmm the whole square plus Ctt the whole square, the whole thing raised to 1 by 3. So these are the two equations we are having for finding out the diameter of the shaft, and we can take this value of sigma and tau, the material stress limit that can be taken from the data book. The Cm, that is the combined fatigue and shock loading factor for bending moment, and Ct, that is the combined shock and fatigue factor for torque. This also we can take it from the data book. All these other values, that is the bending moment M and the torque T and M, this we have to find out. So these are the data we are having, and we will see how to find out bending moment and the twisting moment, that is torque and M.